If the mobile phase reservoirs are not inert enough, if the mobile phase reservoirs are not inert enough, they are going to change the property of the mobile phase. The property of the mobile phase is going to be changed if they are not inert. Means uh, there will be any unwanted chemical interaction of the species present in the mobile phase reservoir and the species of the liquid which has been filled into this reservoir. And reservoir filters will be having the capacity to remove 2 to 10 millimeter particulate matters. So because it must be free from any particulate. And degassing system will be given the provision with the vacuum filtration or purging with either nitrogen or helium gas. What I have showed you is purging with helium gas. Ultrasonic purging will also be done under the vacuum system. And these solvent reservoirs are placed at the top of the instrument because it will be very easy, just like a overhead tank, overhead water tank. The liquid reservoirs are placed at the top of the instrument, so it will be elevated. So therefore, in liquid chromatography, the solute molecules are separated because of the partitioning of the solute between the stationary phase and the liquid mobile phase. Two important points you need to remember while performing liquid chromatographic separation. So separation will be done in two ways. First one is the isocratic elution and the second one is the gradient elution. In isocratic elution, the solutes molecules are going to be separated by using a single solvent or mixture of solvents of same composition as a mobile phase. Either we can use solvent A as a mobile phase or 1:1 mixture of solvent A and B as a mobile phase for the separation of all those solutes which are present in the sample. Assume 10 solutes are present in the sample, all those 10 solutes are going to be separated by using only one mobile phase. Only one mobile phase. That mobile phase may be a single solvent or a mixture of two solvents or mixture of three different solvents, whatever it is. So constant composition will be maintained. Constant composition will be maintained if you use three different solvents. If you use two different solvents, constant composition will be maintained for the separation of all those solutes. So only one solvent reservoir is enough because you will mix the solvents, two different solvents if you are using, you will mix them at some proportion. You will take them in the solvent reservoir and you will fix that to the pump and its journey will be fixed towards the chromatographic column. So you will get the chromatogram at the end, and these chromatograms are obtained by the elution of the solute using the same mobile phase. If there were 10 solutes, all those 10 solutes are eluted by using the same mobile phase. This is called as isocratic elution. Gradient elution means you assume 10 solutes are present, 10 solutes are present. You elute two solutes by using one mobile phase. You elute other three solutes by using other mobile phase, and you elute some other solutes by using some other solvents as a mobile phase. So two or more solvents are used, and these solvents are selected based on their polarity. Based on their polarity, because polarity index is very, very important in order to decide the successful elution process. Once the elution is begun, the ratio of the solvents are varied by programming. So we can vary. For the elution of two solutes, you can use 1:1 solvent A and solvent B. For the elution of other three solutes, 0.5 is to 0.5 is to 1 of solvent A, solvent B, and solvent C respectively, like this: 50 ml of solvent A, 50 ml of solvent B, and 100 ml of solvent C. You can mix together. This can be done by simple programming. So different mobile phases or different solvent systems which are used during the elution process in order to enhance the separation efficiency, and this elution is called as gradient elution. Gradient elution. So the advantage of gradient elution is in order to enhance the separation efficiency of the solutes. You can see this chromatograms. Two chromatograms I have presented here. One is for the isocratic elution and other is for the gradient elution for the separation of these 10 molecules right from benzene to hexachlorobenzene. If you look at the elution here, assume a single solvent or mixture of two different solvents of constant composition was used for the separation. Uh, the analysis took 30 minutes in order to elute all those 10 solutes. The analysis took 30 minutes. Of course, despite taking 30 minutes, despite taking 30 minutes, there were most overlapped solutes. There were most overlapped solutes are seen during the isocratic elution. There is no peak separation. Since the peaks are not separated well, the resolution is impaired. The resolution is impaired. So, isocratic elution is not going to be more useful for the separation of these 10 molecules or these 10 solutes. If you go to the gradient elution, means you might have used different mobile phases or a mixture of different liquids for the elution of group of 10 molecules, individual group of 10 molecules. Less than 15 minutes was required to elute the 10th molecule, but the resolution was improved. The resolution is improved. So just for this reason, the gradient elution will be advantageous when compared to isocratic elution while performing HPLC separation. And next, pumps are very, very essential while performing the separation by HPLC. And what kind of a pump we will use in HPLC? The material which are used to construct the pumps must be inert towards the solvents what we are going to use, because their interaction with the solvent must be negligible, must not be expected. The interaction is going to be taken place, the solvent composition is going to be altered. Therefore, the polluted solvent is not going to be useful as a clean mobile phase. Another requirement is pump must have the ability to create the flow rate at least 10 ml per minute. So for a minute, at least 10 ml of the mobile phase must be passed towards the chromatography column. This is the requirement of a pump while choosing it. And it should deliver precise and accurate flow less than 0.5% relative error. The relative error when compared to the flow rate of the previous flow to the next flow, two neighboring flows, the relative error must be 0.5%. The variation should be 0.5%. At least 6,000 psi pressure must be able to be created. Pulse-free flow must be obtained. If pulse are obtained, they are going to damage the separation process. And they must have low pump head volume. So because we will be using very lesser volume of the sample solution, and even the mobile phase will be used with a limited volume. Therefore, the pump head volume should be very less. It should be reliable. So accuracy, reproducibility, selectivity, everything must be seen while choosing the pump. So after looking at the requirements of the pumps are of four types: reciprocating pumps, syringe pumps, constant pressure pumps, and pneumatic pumps. Reciprocating and syringe pumps and even constant pressure pumps are mostly used pumps in HPLC separation. Let us see one by one. Reciprocating pump, which will be having 1, 2, or 3 pump heads. It is advantageous to have more heads because the pulses will be less if the heads are more in a pump. If the heads are more in a pump, the pulses will be less, so pulse dampness role will become minimum. And the head volume will be from 50 to 250 milliliters only. 50 to 250 milliliters in reciprocating pumps. And it will be having a short piston stroke. This piston stroke is capable to move the liquid front and rear. This piston is able to move. During the movement of this piston, there is a creation of the pressure. And because of the pressure is created, movement of the liquid through the chromatographic column, through the capillary. And the inert pistons, the pistons are going to be inert. We can say supply pistons are going to be used because they are not going to be degraded. So with the time, the functioning of the piston will be intact. There is no any modification of the nature of the piston, irrespective of the material what is used, and it can be used continuously. So because that will be connected to the sample reservoirs, we need not to refill. We need not to refill the liquids during the separation process, and it can be fixed with the pulse dampeners very easily. Therefore, these pumps are very advantageous. You can see the overview, the schematic of the reciprocating pump. The reciprocating pump is having a primary component of a piston. You can see a piston here, and this piston is connected to the motor. Motor will be always driving in order to make this piston move. In order to make this piston move, and here the solvent connection will be given from the solvent reservoir, and the other terminal of this reciprocating pump will be connected to the column. When the pressure is created by means of the movement of the piston, when the pressure is created, the solvent is going to be sucked from the solvent reservoir, and it will be moving towards the chamber which is present here, then ultimately towards the column. Here, the solvents are going to be mixed. If you are going to use different solvents of different composition, they are mixed prior their movement towards the pump. So the solvent in different composition or constant composition or a single solvent, they are made to move towards the column by means of a reciprocating pump. The movement of the solvent can be seen by means of checking valves. These two are the windows. These two are the windows. We can make use of these windows in order to see the movement of the solvent. And of course, there will be pulse dampener. This will destroy any pulses created unnecessarily, and pulse-free mobile phase front, pulse-free mobile phase front will be moving towards the chromatography column. So this is about the functioning of reciprocating pump. A motor-driven piston will be creating the pressure in order to make the solvent to flow towards the chromatography column at a fixed pressure, at a fixed flow rate. And this is the commercially available reciprocating pump. You can see the terminals here, and by means of the terminals, we can make the mobile phase to move towards the chromatography column. This is a motor. This motor will be driving. This motor will be running in order to create the pressure. At the created pressure, the solvent will be sucked from the solvent reservoirs, and ultimately we can connect this at the fixed flow rate. We can regulate, we can monitor by means of this flow regulator, and ultimately we can connect to the column. So this is the terminal to connect into the column. Next, syringe pumps. These syringe pumps are also widely used pumps in HPLC. Whenever the constant flow rate is required, they are just like a syringe. So you all seen the syringe. Syringe is capable of holding several milliliters of the solvent in that. So the volume of the solvent will be definite and fixed. So whenever a definite volume of the mobile phase is moved at a fixed flow rate, and this condition is required to be fulfilled, then we will use syringe pumps, because they will produce constant flow rate always. They don't create any pulses, therefore they are going to create non-pulsating flows, but they create very low flow rates from 1 to 100 ml per minute. Whenever lesser flow rate is required, we are going to use these syringe pumps. Whenever high flow rate is required, we are going to use reciprocating pumps. And these are applicable only for isocratic flow only, because we cannot connect the terminal of this pump to the multiple solvent reservoirs. So only a single solvent reservoir can be connected to this pump, therefore isocratic flow can be created. And of course the refill is required, because this is a syringe like object. Refill is required for the mobile phase in order to introduce into the chromatography column while creating the pressure. So each and every refill will be occupying up to 50 milliliters of the mobile phase. You can see here, this is a pump, syringe pump. This is having the object just like a syringe, and this is a movable object in the syringe. In order to create the pressure, this piston will be made to move, and the mobile phase will be made to fill into this particular syringe. Then it will be made to pass towards the chromatographic column. Constant pressure pumps are used in order to create the constant pressure, but not the constant flow. So you must remember this. Flow rate will not be constant, but the pressure will be constant. These constant pressure pumps are capable to create very, very high pressure. So whenever if we wanted to create 4,000 to 6,000 psi, 4,000 to 6,000 psi pressure, we will be using these constant pressure pumps. And of course, they will produce stable flow during the delivery. And we can stop the flow and we can refill while using these constant pressure pumps. They are very, very low cost pumps when compared to rest of the other pumps. This is the schematic of constant pressure pump. There are the two terminals. So one is to the mobile phase reservoir and other one to the chromatography column. A motor will be running always to create a constant pressure, but not the constant flow. You should remember. And while creating this constant pressure, always we cannot vary the pressure during the separation, in between the separation. Once we adjust the pressure at 4,000 at psi, 4,000 psi, the same pressure is going to be maintained throughout the separation while using this particular pump. So therefore, this constant pressure pump will be having the packed schematic view like this. So there are terminals, you can see, one towards the column and other towards the solvent reservoir. Another one is a pneumatic pump. The advantage is it will be having collapsible solvent container. If we wanted to make use of a solvent container which can be collapsible after the sample introduction is over, this pneumatic pump is going to be introduced. And other primary characteristic of this pneumatic pump is this pump can be pressurized by means of a compressed gas such as helium or nitrogen. We can pressurize. So gases are filled tightly into a container, and these compressed bags can be used in order to create the pressure by means of this pneumatic pump. So this pump is inexpensive and pulse free, but which suffers from limited capacity, pressure output. Pumping rates depends on solvent viscosity. You know this because viscosity, if it is more, the pumping rate will be more in order to create the greater flow and greater pressure. And therefore, this is not adaptable for the gradient elution because collapsible solvent container will be used and compressed gas is required. The gradient elution means different variety of the solvents are going to be used. Therefore, we cannot connect this pump for multiple solvent reservoirs. Multiple solvents are required in order to perform the elution by gradient technique. Therefore, this pump is not suitable for gradient elution. So these are the four important types of pumps: reciprocating pump, syringe pump, constant pressure pump, and pneumatic pump. Most commonly used is reciprocating pump because its advantage of creating the pressure, high pressure and high flow rate, and we are able to connect for the different number of mobile phase reservoirs. Therefore, gradient elution will be possible. That is the most advantage of reciprocating pump. And apart from whenever a limited flow is required, we will be using constant pressure pump, where we cannot attain a greater flow rate. Of course, the constant pressure can be maintained throughout the separation. On the other hand, the pneumatic pump is not applicable for the gradient elution, but if we wanted to use the collapsible solvent container, then we can go for this pneumatic pump. This is a cross-sectional view of the pneumatic pump. A motor will be present, of course, in order to create the pressure. So the terminals, one for the column and one for the solvent reservoir. This is the cross-sectional view of the pneumatic pump, and you can understand in a better way by looking at this. Mobile phase reservoir will be connected, and a piston will be moving by means of the motor, in order to create the pressure. Then at the created pressure, the effluent from this terminal will be moving towards the chromatographic column, and this will be carrying the mobile phase towards the chromatographic column. So this is about the pneumatic pump. And in order to introduce the sample injection system is very, very important. So as we have discussed in gas chromatography, we will use wall loop injectors. Wall loop injectors by means of an hypodermic syringe, hypodermic micro syringe, we can introduce the sample into the chromatographic column. We can introduce the sample into the chromatographic column. So this is going to be the wall loop injector system, which is allied in the HPLC instrument. You can see here load and inject, inject and load. This is a knob able to be shifted, able to be rotated, able to be moved, able to be moved. So this is the port in order to introduce the needle of the micro syringe. Hypodermic micro syringe will be having a needle. That needle can be penetrated into this port. Before introducing the needle into this port, you have to adjust the positioning of this knob to the load, to the load. Then you have to introduce the syringe needle. Then if you rotate this towards the injection mode, then you introduce the sample to the column. Means it will open the loops for the movement of the solution towards the chromatographic column. You can see here very clearly, this is the needle of the injector. Once it is introduced, before bringing the knob into the injection mode, whatever the sample introduced, that will be going as a waste. It is not going towards the column. It is not going towards the column. So therefore, after the injection is over, if you bring the pointer, if you bring the loop towards the injection mode, the introduced sample is going to travel towards this loop and it is going to be combined towards the chromatographic column. See here, arrow mark. Okay, so from pump the mobile phase is coming. Mobile phase will be carrying the solute which has been introduced, and it will be combining towards the chromatographic column. So therefore this wall loop injector will be playing an important role. So when you load the sample, if you are unable to, or if you have not brought the loop towards the injection mode, whatever the sample introduced, that will be going as a waste. You can see by means of this arrow mark. So once the sample is introduced, injected, loaded, once the sample is loaded, you have to bring this rotor wall towards the injection mode. Then introduce the sample is going to join the mobile phase front, then it will be moving towards the chromatographic column. So this is how the rotor wall or wall loop injector will be functioning. This I have already shown while explaining the gas chromatography. So this is how a syringe can be made use. A needle can be penetrated into the port. This can be rotated either towards the left or right. If you rotate this towards the left, that is for loading the sample. If you rotate this towards the right, this is for injecting the sample. So take the sample in the hypodermic syringe, penetrate the needle into the sample port, rotate the knob towards the load, right? Then you dispense the liquid which is present in the syringe. After dispensing, you rotate the knob towards the injection mode. Now the sample has joined the mobile phase front. So the mobile phase is now taking away the solute molecules which have been introduced, which were present in the sample in the injection port. So this is the wall loop injector, what I had showed while explaining gas chromatography. And in order to introduce multiple samples, there are auto injectors are also available in industries. Various industries are making use of these multiple injection ports. So you can see 5 to 6 injection ports miniature auto samplers are available here. This I have already shown while explaining solid phase extractors. So robotic workstations, XYZ liquid handlers and robotic workstations can be used in order to perform the extraction by solid phase extraction technique, where we can introduce so many number of samples, more number of samples, so that the analysis will be over within the stipulated interval of time. Very less interval of time may be enough, sufficient. So number of samples can be introduced in different injection ports here. So these are individual injector ports where we can place the sample in the liquid form, and we can fix the time duration one by one. The samples are going to be chosen by programming or by the instrument itself, and the solution sample solution analysis will be over within a small interval of time. So continuous injectors are also be used. They are operator free. As I told you, we can adjust the time interval. We can adjust the time interval for choosing the sample at different time intervals. Comparable precision and accuracy can be expected. Of course, this is automated, highly automated, much expensive, and up to 100 samples and standards can be processed, because a microprocessor control will be available here, just like a microprocessor unit, what you can see in the flame photometer, what we have in our laboratory. Once the sample is aspirated, sodium, calcium, potassium, lithium, and strontium, at a time, all these elements can be detected by means of that microprocessor. So like this, 100 samples, if you have introduced in these injectors, it is very easy to the microprocessor to select the samples at different time intervals. Okay, so after sample injection systems, the columns. The columns, as I told you, the columns are the art of the chromatographic instruments. So if you are unable to choose appropriate column, the separation process is going to be disturbed to the maximum extent. So you have to be very careful while choosing the stationary phase. Column is nothing but the stationary phase. If the stationary phase is not suitable for the separation process to be completed, then the separation is not going to be efficient. So you have to be very careful and highly knowledgeable while choosing the column. So the liquid chromatography columns are normally constructed by stainless steel. Uh, they are also heavy walled glass tubes. They're also heavy walled glass tubes, and the glass tubes are restricted to pressures up to only 600 psi. 600 psi, because they prone to break. They prone to break. Therefore, if we wanted to use the column at the pressure above 600 degree 6 psi pounds per square inch, above 600 psi, we cannot use the glass columns, but we can use stainless steel columns when the pressure is going to be maintained beyond 600 psi. There are two types of columns are used in HPLC. One is analytical column and other one is guard column. Guard column is also called as pre-column. PRE column, pre-column. Analytical column is the heart where exactly the separation is going to be taken place. Analytical column is the one where the exact separation is going to be taken place. So this will be having a length from 30 to 10 to 30 centimeter. Even we can combine 2 or 3 columns in order to increase the column efficiency. So minimum 10 centimeter to 30 centimeter column we can use. These columns are straight. Of course, we can add the length by coupling 2 or more columns. The internal diameter will be from 4 to 10 millimeter, and the packing material means the stationary phase will be having the particle size from 5 to 10 micrometer. 5 to 10 micrometer. The most commonly used column will be having the dimension of 25 by 4.6 millimeter by 5 micrometer. Why do we say these 5 micrometer particles? Means these columns are available in the market. Ready columns are available in the market. So where they have used the stationary phase of each and every particle with the particle size of 5 micrometer. That's it. So these type of columns are able to yield 40,000 to 60,000 plates per meter. If you use a meter of column, up to 60,000 plates, theoretical plates are going to be obtained. These are the images for the glass column, stainless steel columns, what we can use as analytical columns. Glass column, the advantage of glass column is we can see the band separation inside. If there are colored objects are available in the sample, we can see the separated bands. If the species is colorless, we cannot. Of course, we can see the movement of the liquid through the column. However, the stainless steel columns are going to be used most commonly, and the packing material will be maybe like this, or which may be a modified one other than this. This is a silica based packing material which are used in these columns, irrespective of the material which is used to construct the analytical columns. This is going to be the material. Silica, a group of stationary phases are used. This is a trimethyl silyl silica, and this is also other modified group in place of hydrogen of OH group. This OH group is available freely. So if OH group is available, there is unwanted adsorption is going to be happened. So you must be very careful. So this is the type of the analytical columns. Guard columns. As I told you, guard column is also very important in HPLC because these guard columns are required in order to remove any irreversibly bindable species present in the sample. Of course, if some species are present in the sample, they are going to bind with the stationary phase. We cannot remove them from the stationary phase during the separation. So that type of solutes can be made to bind with the stationary phase of the guard column. You do remember, the stationary phase of the guard column will be same as the stationary phase of the analytical column. So that any irreversibly bindable species will be binded with the guard column, or even the stationary phase may also be different. So this guard column will be present before the analytical column and after the sample injection port. The guard column of this type will be present before the analytical column and after the injection port. So once the sample is introduced, any impurities present in the sample, they are going to be binded with the stationary phase of the guard column, and the particulate matters are also going to be removed. And if there are any unwanted species present in the mobile phase, they are going to be stayed in the guard column, and the samples with the respective suitable number of solutes are going to be moved towards the analytical column. So this is the HPLC column or analytical column where the exact separation is going to be taken place. Then the solutes, after getting separated in the analytical column, they will be moving towards the chromatographic detector. So you can see here the performance efficiency of the HPLC for the separation of 8 compounds like paraxylene, anisole, benzyl acetate to diethyl phthalate. So high speed isocratic separation has been done by means of 4 centimeter column of inside diameter 0.4 centimeter, and the packing material is 3 micrometer particle size Perizov, which was spherical in shape. 4.1% ethyl acetate in NaHN was used as a mobile phase. So ethyl acetate in NaHN, mixture of ethyl acetate and NaHN. NaHN is non-polar. So non-polar mobile phase and polar stationary phase is used here. So by using this, we can separate 8 compounds within 15 minutes. 15 seconds, you can see 15 seconds. So liquid chromatography and bonded phase chromatography is under the partition chromatography in order to classify the liquid chromatography under partition principle. Liquid stationary phase is used and bonded phase stationary phase will be used. After looking at the structure, if you take silica, as I told you, silica can be modified to any extent by chemical modification, by removing any trace metal impurities, followed by treatment with either alkali or acid. So silica can be obtained to the required level so that either polar or intermediately polar or non-polar stationary phase can be obtained for the use in HPLC. So if a liquid is present in the silica surface, that liquid is going to modify the polarity, then that is going to be liquid-liquid chromatography. If a bonded phase, silica bonded stationary phase is used, the solute molecule is going to be bonded over the surface of the bonded stationary phase. So that is called as bonded chromatography. You can see here in this particular slide, here R group, you can say R group. If R group is modified by methyl, octyl or octadecyl groups, means the modified silica it is methyl, octyl or octadecyl group. You can see the time limit for the separation of these 6 compounds, uracil to tallinn, 8 minutes with overlapping, 16 minutes with overlapping between compound 3 and 4. There is no overlapping, but time up to 24 minutes. So if you increase the length of the alkyl chain present in the modified silica or bonded silica, we can increase the resolution of, but longer analytical time may be required. So this is how modified stationary phases are required. Here, the mobile phase modification will be done. Acetonitrile water, acetonitrile tetride of furan water, like this you can see. So we shall stop here because time is going to be over. So if you have any doubt, so I am happy to answer. So are you clear about the presentation?
Yes, sir.
So I shall stop here. Tomorrow I will continue from the
Yes. So
HPLC
God
and
column
HPLC.
and
Yes.
so God column and answer explain once.
Guard column is also called as pre-column, which is used to remove any irreversibly bindable solute present in the sample or any unwanted species present in the mobile phase. These guard columns are placed before the analytical column or after the injection port. Okay, and the stationary phase present in the guard column will be same as the analytical column, and sometimes it may be a different. Sometimes it may be a different.
Yes. Analytical.
Okay.
Okay.
Any other questions?